how does choosing a larger value of the Gaussian height result in slower convergence? We have large, okay. Yeah, what I was meaning here was the bias factor. It's the bias factor that determines how, let's say, how fast we converge or how slow we converge. Because let's say the bias factor determines how much we dampen the height, Gaussian height. So if we dampen it very slowly, then like it will take longer. And also you can think of it like that. The more we enhance the fluctuations, the more bias we need to build. So that will take more time. So the main thing is that you should choose a bias factor large enough that you enhance the fluctuation and you have good sampling, but not too large, because otherwise it will be slow convergence. Okay, so let's then go to the tutorials. Let me know if you don't hear me clearly, because I need to change a bit the setup and use a different computer for this. So I hope the mic should be in a good location still. Okay, before we do the tutorial, you have to make sure that you have the latest changes to the GitHub repository pulled in, because I made some changes to the notebook, so you have to make sure you have the latest changes. So if you go to, let's say, on demand like yesterday, and then you initialize a new, let's say, secure shell, and you go, let's say, to the you go to home, you go to the folder that you cloned yesterday, and now what you do is that you do you might want to do first is you go to git status. Then you will see, for example, most likely if you're doing the tutorial yesterday, the file from yesterday has been modified. So if you would try to do a git pull, it will complain, because that might complain. So what you can do is that you either can just add this and commit these changes to your own local repository, or you just can copy it to a new file. I mean, you could go here, go to Monday, copy toy model, and do save, something like that. Or better, what you can do is that you can just add to git add and add this to your current local Git repository. Okay, sorry, wrong path. And then you can git commit -m and say my changes. Monte's notebook. So now you would have this in your, let's say, local repository. So what now you can do git pull, and that should hopefully pull all the latest changes to your repository. You might enter this prompt here. Then you just do this is a VI prompt. You just do 2 columns W and enter, and then you have written the file, and you do two columns and Q to exit the VI. And now you should have all the latest changes to the Git repository. So you should have the latest version of the Jupyter notebook that we'll be working on today. And then in my case, I have the folder here. I go to this folder, and I go to the Tuesday session. And then you can see a bit of different files. We have the slides from this today's lecture, README files, and the Jupyter notebook for the tutorial. And then we have the files that we use for the tutorial. So I should mention now what we do in this tutorial is that we will do all the simulation in the Jupyter notebook. So we will do all the interaction with the simulation, the setting up of the simulation, and input files in the Jupyter notebook. This is not something that you will do normally. Normally, you would interact with the simulation using a queuing system and so on. But here we'll just do it for the educational purposes, everything in the Jupyter notebook. So we will, let's say, we can always just stay in that Jupyter notebook and we do everything there. So But however, I can mention like all the analysis that we will do, you could do that in a Jupyter notebook for a simulation that you've run previously and so on. So you can use similar, let's say, scripts and so on, as shown here for doing this. Okay, let's then just start by running through the cells. So we start by just importing a few Python scripts that we'll need, and then just checking which modules are loaded. Unfortunately, I did not find a way to load the modules for Plumed and GROMACS throughout the notebook, so it has to be done each time Plumed or GROMACS is run. But that's not a big issue because I've, let's say, automated everything. And the important thing is that, as I say, this notebook has been tested to run on this on demand. And here you should make sure that you're using the default kernel, like the Jupyter Notebook kernel for this run, like shown here. So you should be using this kernel here, not using this kernel here that we were using yesterday. Okay. So as I say, the first thing that we need to do is just to define the Plumed binary and check sure that this is what is working fine. So this is some of the things that you might need to change if running in a local resources. So in this case, because we're using a Plumed binary from a container, which was like compiled for this workshop, we will use this command for the Plumed binary. In most cases, you can just comment this file and use just Plumed directly, and then all the resulting script should work fine. And then so this just define the Plumed binary, and then for not having to write out the Plumed command every time, and like this because it's very long, I define like a command to run the Plumed commands. So this is just a function, a Python function that will create and run the Plumed commands for us. So then we just test that this Plumed command works. And if everything is fine, we will just get something like here, just the help message for the Plumed, and it should work fine. So this should work fine on the open. Then we also need to define the GROMACS binaries. So normally you have like two different binaries for GROMACS. You have like the GMX, which is like with the different tools. And then you have the MD run, which is the Polygon Dynamics run. And it depends a bit of how your GROMACS was set up, how it will work in practice. But these are the values that work fine on this resources. And I believe if you are able to install this GROMACS with Plumed from this like this content channel, that this should be the same commands. So here, like if you're doing it on your own local resources, you might need to define these variables here. So the main thing, if you're running on local resources, you just might need to change these variables here for the GROMACS, and for the Plumed, and everything else should be the same, because I cannot try to wrap it up in kind of in wrapper so it like doesn't so you don't need to define it in multiple places. And also, unfortunately, every time we call GROMACS, we need to load let's say in each cell we call GROMACS, we need to load the modules again. But I just did it here so that this is only done if you're running it on bridges. Otherwise, you will not try to load the modules. So now,
Omar, do you mind repeating how many nodes and threads you requested so I can put that in the notes?
I'm asked for this simulation, I asked for one MPI process and one thread. Because this is
the Jupyter session that you requested from on demand. Was that just one?
Yeah, just one. Okay, thank you. So because this is a very small system, and so it like actually if you try to run it on more than 2 or 4, let's say 4 processes, it will most likely run because the domain composition doesn't work so well with small systems. So most of the time you can just use, let's say, 1 here. So this works fine. And if I try to run it on 2, I think there was no performance benefit. So this is a quite small system that we use here. Okay, so now we just again test if this like GROMACS interface run. And if you get something like here, in your, let's say, local resources, you're in luck and everything should hopefully work fine. But unfortunately, I didn't manage to a chance to test it carefully on the Conda resources, but it should work fine here. And then we just define this just to have larger figures. Okay. And the next function is just something that I added is like if you rerun this notebook again, that this is just a function that will like back up all previous exercise files and move them to a different folder. So you don't overwrite files, just to have a cleaner setup for each time you run this notebook. Okay, so the system that we will consider here is a very simple system. It's like a sodium chlorine ion pair in water. So in this case, we have like one sodium atom and one chlorine atom and like 107 water molecules. So in this case, we are using quite small box just to speed up the simulation. That means also that we are using quite small cutoffs for all the, let's say, short range interactions. So you should be careful that this simulation setup is not really for production runs. It's mostly just for testing, and you need to be a bit careful that you should not use these inputs for like anything sensible. But this here works fine because of this of the system. So, and I say we'll be looking at the association and dissociation of the sodium chlorine ion pair. And here we're running the simulation at 300 Kelvin. So this is just something which we can define just to kind of use it later on. We just calculate the kpt at 300 Kelvin in kilojoule per mole. Just to note that Plumed and also GROMACS, they always use units of energies in kilojoule per mole, distance in nanometers, and time in picoseconds. So if you're working with Plumed, most of the time you'll be using these same units, kilojoule per mole, nanometers, and picoseconds. So this is just one can easily calculate that the kpt at 300 Kelvin is like 2.5. And it's a good value to keep in mind that kpt at 300 Kelvin is around 2.5 kilojoule per mole. And this is something we will use later on when we set the parameter. So what we're going to do now is that we're going to go over at least this first 3 exercises, up to finish exercise 3, and look at the results. So what we're going to do is that we're first going to do an unbiased simulation, and then we're going to do a bias, very biased, the distance CV. Then we're going to look at the reweighting, and then we're going to do a separate meta-dynamic simulation where we bias 2 CVs, the distance and the solvation CV. And also want to show for that how you can restart meta-dynamic simulations. And exercise 4 is something which we'll not probably get to, but we can also play with that on your own. Okay, so I would say always before running meta-dynamic simulation, you would always perform some kind of unbiased simulations, just to monitor the relevant CVs, estimate the fluctuation to obtain the sigma values, and so on. So this is what we do here. So now we have this template folder with all of the different files needed, and we'll just copy that to a new folder. And then we go to this folder, and then we, let's say, look at the different, look at the different files that are available there. So the files that we have here is, let's say, the topology file, this one file here, and 2 starting structures. And there are some other files that we will not really use, but they're also there, which you can also use for, let's say, running simulation later on. Okay, so if you look at the topology file, if you have not seen GROMACS topology file before, they look like here. Just define this force field parameter. We are using OPLS, but you could also use Ampere or any other force field, doesn't really matter. And then it just define, let's say, this solvent molecules and then the 2 sodium atoms. Okay, and then here you have the initial structure. So you can see here that here we have the solvent molecule starting from 1. This is the atomic number, then 1, 2, 3, 4, etc. And you can see that the oxygen or the water is always numbered is every 4th atom. It's number 1, 4, 7, so on. And then we can see at the end, we can see the sodium and chlorine atoms, and they are numbered 322 and 323. And this is, you need to keep this in mind when we define the distances and so on. So when you define new collective variables, you often need to look into the geometry to find what is the relevant atomic number. Okay. So now here we have two relevant collective variables. The first one is just the distance between the two, the sodium and chlorine atom. And that is like, say, defined like here. So in Plume, you define a distance like here. So this is the keyword for the distant collective variable. And you just have one argument for the collective variable, which is just the atom used in the simulation, the sodium atom and the chlorine atom. And this is something which we got from this, from looking at the geometry file. Now, also another motion that collective variable that I want to look at is the solvent, like the collective motion of the solvent. To measure that, we use a coordination number collective variable. So what we do is that we define a coordination number that measures the, let's say, the coordination of the sodium atom with the oxygen on the waters in the environment. So in here, this group A defines the sodium atom, and then this group B defines the oxygen atoms. So here we use a syntax of Plume, which is that you take all atoms from 1 to 321, but by having the two columns and 3, you take every third atom. This means that by this selection tells you that you're selecting atom 1, 4, 7, etc. And here we are using a rational switching function to measure this coordination with some given cutoffs. These are some parameters that have been determined a priori. Okay, so now, before we, let's say, start down by simulation, we need to set the molecular dynamics parameters. And in this case, you would normally do this like in VI, in the shell, you would estimate this parameter, set up this input file, but here we just do it in the Jupyter notebook. And I'm just using this kind of cat end of file syntax to generate this file. So this is a called MTP file for GROMACS, which determines the different parameters used. So here is the, like, say, time step and the different parameters. So the main parameter that we need to worry about will be the number of steps. So here we want to run for, let's say, 10,000 picoseconds, which means that 500,000 empty steps, because you're using a time step of 2 femtosecond. So this is what, and then we have the cutoffs, then we have like the temperature and some other parameters. But like, don't need to worry too much about these parameters. These are all quite general parameters, apart from the cutoffs used here. Here we're using, let's say, much smaller cutoffs than you would use in a proper simulation. So now we just generate this file, and then you make sure that this file is here, and then you see this file. So now when we have this MTP file, we need to use that along with the topology file and the initial structure to generate the so-called TPR file. And this TPR file is, let's say, is a file that we will run using GROMACS. So these are the commands that we use to generate this TPR file. We use this GROM-MPP, and that would take all the different files. And that, in this case, we just run, and you would normally, if everything was run fine, this works like here. Okay, so, and now we can see that this file here was generated, so we should be able to start the GROMACS simulation. So next thing is to define the plumed input file. Like previously, I defined this kind of collective variables, and now I want to define this plumed input files. So now, so this is the input file that we define for plumed. So this is the exact input file that we define. So the first thing is just to find the different collective variables. So I define the distance. I use the distance action or keyword, define the atoms, and then this one here, by having this dist and 2 semicolon, means that this is the label I use for the distance, and I can refer to that later on. So and then I define the coordination, and I give also a label to the coordination. So this syntax or for this one here is the same way to give a label to the collective variable. And then we can like use this collective variable in different other actions, where we use this arg before argument, where we add, let's say here, we use this print statement that tells us that every 250 empty steps, we will print out this collective variable to a callbar file with this given name here. And yeah, also what we're using here is that to, let's say, to reduce the, let's say, a bit the entropy in the dissociated state, we add the upper wall on the distance. This is just to make the, let's say, the result a bit slightly more, yeah, just to like say reduce, so we're not exploring too much of the distance. This doesn't really make much difference from the result. It's just a good way of, let's say, so slightly reduce the time needed to convert the simulation. But this is more, let's say, for educational purposes that we add this upper wall. But we can just think of this is just a part of the system that we are simulating. So we're not really, we just keep it as it is and not really think about it too much. So now, we, as I say, we use this cat and file syntax to render the file. Now you can see that we have prompt output. And yeah, we see that we have this prompt output. So now the next step would be to run the simulation. And that is what we do here. So this is, let's say, where we run this simulation with this empty CoMSE empty run binary. And here you might have something like it will not work. That might, if you're using a local resources, it might not work. But we have to see with that. So now what we can do is that we just run the simulations, and now what you see is that you don't see anything happening. But actually what you can do now is that you can go to your, let's say, folder. What's going on? Let me see. I think it's because I zoomed in. Okay, so now if you go to this folder where we run the simulation, exercise 1, you can see that we have this callbar file that is being written out to. And you can see the simulation is running. So we are having information written out to this callbar file during the simulation. But we don't see anything happen in the cell. But there is things, the simulation is going fine. And then we can see the same with this log file here, that it is progressing as we want. In this case, the simulation should take, let's say, 1-2 minutes. It should be relatively fast. And you can see like that, yeah, that this callbar file has like some like a time series in it. Okay, now the simulation has finished. So now we have finished this run here. Okay, so as you can see that the simulation has generated various files. And yeah, and in particular, the main file to look at is this callbar file. And if you look at, let's say, the initial header of this file, you can see that it has like different variables in it. And you can see in this first line here is a comment line, and it gives you, let's say, the name of the different fields. So it's telling you that the first field is the time, then the distance, and then coordination, and then some variables related to the wall that we put on. Okay, so now what we can do is that this is a text file which we can just read in using like any given like numpy load text. So in this case, we can just plot the function here. So now what I did now is that I just took this callbar file, I read it in using numpy, and now we can plot it using these commands here. And yeah. And yeah, so this is how you would plot it. So like you can see that because like Python syntax is that a 0. So in this case, the time will be like 0. Time is column 1, but it will be 0 in the Python syntax, and the distance is column 2. So in this way, we can plot it like in this way shown here. So then we can see that, okay, in this case, in this like 1,000 picoseconds, there are some transitions. So the system is not ultra slow, but we see some transition between the two states, but not that frequent. So we can see there are some transitions, okay? And then now we can calculate the distance and so on. But not to have to write this type of code again and again, I will just define two Python functions that one reads the callword file and one just plots the callword file. And we can use this again to look at the, let's say, the distance again, and we can see a few transitions between the two states. Okay, so what we want to do now is that now we run this unbiased simulation, and we want to use that to estimate the, let's say, the sigma used for the meta-dynamics. But there is one problem here in this case, because if you would have like just stuck in one meta-simple state, it would be fine. We could just calculate the standard deviation from that time series, it would be fine. But now we have like two different states and transition. So we need to make sure that when we calculate the standard deviation, we are calculating the standard deviation for the two states separately. So we need to make sure that when we calculate the standard deviation for this one, we do it separately from this one. Because if you would calculate the standard deviation for the whole time series, we would just get too large standard deviation, because it's a bimodal distribution. So I just wrote a simple code here where you kind of introduce the separation of the distance. And in this case, let's say, you separate the distance into, let's say, associated and dissociated state based on this distance here. So I select that around this value here, we would separate the two states. And then you can like calculate the standard deviation separately for the two different states. And this, I can also plot it here just to make sure that it is separated in two states correctly. So here we can see that using this procedure code here, you can take a look at it in your own time, how it is done, is that you see like now it is separated between the two states. So now we can see that if you look at the associated state, that has a standard deviation of like 0.014. While the standard deviation of the dissociated state is like it's much larger. So here you have to be careful which value you select, because you will need to select a sigma for your Gaussian corresponding to the, let's say the smaller standard deviation, I mean the state with the smaller fluctuations. Because let's say if you would use this value for the standard deviation of the Gaussian, this would be way too large value to when we deposit in the like associated state which has less fluctuation, because in that case we just smear out the fringe surface and most likely not get good results. So you need to be a bit careful with like we selecting the standard deviation. So in this case, we select like the lower value of the fluctuation, which will be this one. So in this case, I would say one could maybe use a value of 0.1 or 0.01 or 0.02. And I tested it and I found like better to use 0.01 in this case. I think 0.02 slightly skews the result, because then it might be a slightly too large for the small associated state. Okay, so yeah, so we will use this value here for the standard deviation. Okay, so before continuing, we should look at the behavior of the solvation CV, which is the third column, and that we can see here. And this is the coordination number of this, or the solvation of the sodium atom with the oxygen on the water molecule, with the oxygen of the water molecules. And you can see there is some transition here. And what we can also do is that we can look at like how these variables are correlated. And you can see here that there is correlation definitely, because like in the associated state, you have like coordination number of, let's say, 4 to 5 to 6, while in dissociated state, you have like larger solvation value. This is of course understandable, because when in the dissociated state, the sodium atom can like coordinate with much more of the water molecules around it. Okay. So now we have done this on-bias simulation. So the next step is to bias the distance CV. So then in this case, we will just go again to the top folder and create a new folder for this exercise. So we'll create like exercise 2, and then we go to this folder. And now we'll do, let's say, 10,000 picoseconds. And so we just need to change this value here that we have done so far. That's already done. And now we can just generate the different files for the chromatograph. So now the main thing is to define the meta-dynamics action that we use for the meta-dynamics. So here, so like the input file for Plumed is exactly as before, as shown here. And then we add this meta-dynamics action here, and with the different values. So the main thing is that, okay, we just add a label to the meta-dynamics action, just so can we refer it later on. And then we add this with the arg, or for argument, just define which CV we're biasing. Pace tells us how often we add the Gaussians. Here we use 500, and 500 is around, let's say, add Gaussians every 500 empty steps. This means like every 1 picosecond, which is a typical value. Sigma is the value that we determined earlier. And here we use a height of 1.25. This is like 1/2 of the KBT. And this is a reasonable value in this case. And then we use a bias factor of 5. And that leads to reasonable results. And then there's like one important factor that when we're doing meta-dynamic simulation, is for performance, you should always use a grid in the meta-dynamic simulation implement. Because if you don't use a grid, what happens is that every time you add a Gaussian, you add like one more Gaussian that you need to be summed up when calculate, like, let me put it like this. Every time, let's say at every empty step, you need to calculate the value of the bias and the derivatives. And every time you calculate the value of the bias, you need to sum up all the Gaussians. So once you have added up a lot of Gaussians, the sum becomes very expensive. So what can happen if you don't use this grid, that you will see as the simulation progresses, it becomes slower and slower and slower, because like your sum of Gaussian is increasing. So the way to solve this is just to represent the bias on a grid. And this has been done in a long while in Plumed, and is quite efficient. You basically just need to define the minimum and maximum of the grid, and then this should be normally fine. Then the code will automatically detect other parameters to use for the grid, that like the spacing of the grid and so on. And then we add this calc RTC keyword, and this enables the calculation of the CFT factor that we use in the simulation. And now we finally have this hill file where we kind of let's say output the Gaussians. Okay, so now, yeah. So this is basically the input file that we use for, like, when we define the meta-dynamics. So this is a very common input file in Plumed. You basically you define your collective variables in this way here, and then maybe some other actions, and then you define the biasing method, and then you define the print statement that will print everything out. And you have to make sure that you are printing like all the meta-dynamics information out during the run, because if you don't do it, it's not written out. Unless it's specifically stated in the print statement, the collective variables are not written out to the callback file. So you always need to add that. Okay, so let me see. So this is like, of course, in many cases, you can have much more complex collective variables than here. For example, it could be, let's say, collective variable that depends on other collective variables and so on. But here we're using relatively simple collective variable. Okay, so now we just generate this Fluent file, and then what we can do is just start the simulation. So, okay, there's something. Okay, there was something which I forgot. Now it didn't work for some reason, and probably because I was having. Oh. Okay, very good. I forgot to do this, so I was not in the wrong folder. Maybe just yeah. Okay. So I was doing everything in the wrong folder. I forgot one of the. Okay. Okay, now the TPR file was correctly generated. Okay, I need to generate the Fluent input file again, so it's in the correct folder. Let's make sure that we are in the correct folder. Okay. Okay. Now all the files are there, and now we can start to run the simulation. Okay, so this simulation, as you can see, we don't see any output from the simulation at the moment. So in this simulation, if you would, but we can still check it is running. So if you go to like the shell and you go to exercise 2, you can see if you do, let's say, tail on the color file, it is being written out. And now it should be written out. And also this hill file, hills.data, is also been written out. And you can see here we are adding this Gaussian every picosecond. So in this file, we will have basically this hill file. We'll have like the time, the value, it's the value of the distance of the coordinate, and then we also have the height of the Gaussian. And also we have like the bias factor and the sigma, and other parameters which are needed to reconstruct the bias potential and the free surface. And you might see here, for example, that the initial height is not the same as we used in the input. That's because it's already been scaled by a factor so that if you sum up this Gaussian, you will get the free surface and not the bias. But this is a detail which is not really relevant. Okay, so I think this run should take about 10 minutes. So since we are already like at 50 minutes, so I would suggest that we just take a break now and come again at, let's say, 1 minute past the hour, and then hopefully, or then let's say this run should be finished and we can start to analyze the result. Okay, I think you should start again. I think you should take like a few minutes more. But now, if does anyone have any questions about what we covered so far in the notebook? You can unmute yourself and ask if you. Okay, in this, let's say, there's a question. In this example shown, both events are seen to occur in regular unbiased simulation. What if you have a system where transitions are very difficult to occur in regular MD, like a big conformational change in a protein? Would meta-dynamics be a good choice to see the transition and estimate the free barrier between them? Yes, that's definitely the case. So most of the time, the system that we apply meta-dynamics to are much slower than we have here. So this is a case, it's a system that I often have used in the past for testing, and I have to admit that it might not be slow enough system to be, I would prefer to be a bit slower, just to see a bit better the behavior and like, but most of the cases where people are applying meta-dynamics are cases where like you would run unbiased simulation, maybe for like hundreds of nanoseconds, microseconds, and you see nothing happening. and you want to enhance the transitions. So yes, but of course, in this case, you need to identify this collective variable. And that can be tricky if you have like big conformation changes in a protein. So most of the time, let's say, in collective variable, meta-analysis has been used in a wide range of problems. You can see the literature. But as I say, it is often, most of the time, like with rearrangements. Like, so in this case, this is maybe not the best example, but it's a very simple system, and yeah, that you can do. And also, I wanted to maybe use a different system than allantoin peptide that people often use. So I believe this is a reason, let's say, okay, now the simulation run. It took around 15 minutes to run, okay? And now we can start to do the analysis. And now we start to see the more interesting analysis. So, yeah, okay. So now, as I say, it's finished, and now we can start to do the analysis. And yeah, so now we can see that we have this color file and the hill file that has been generated. And now let's look at how this hill color file and hill file look like. So now you can see here in this color file much more different variables. You have the time, distance, coordination number, or the solvation CV. And then you have the bias potential from aerodynamics acting on each instantaneous time step. So this is the bias potential directly. Like for a given, let's say, sample, like here, this would be the bias potential that is acting. Initially, of course, this is 0, and then it grows. And then you have this R bias. And this R bias is this kind of renormalized bias potential, which is this bias potential minus the C of T. We'll look at that better. And now, and the Hills file just has like this kind of the added Gaussians. In the meta-analysis literature, often these Gaussians are called hills. And this is why we call it as a hill file, and why it's called hills in like the hills.data in our run. Let's now look at the time series of the distance. And now you can see we have much more frequent transitions than before. And very quickly, the system is like nearly diffusive. So you can see like previously, like the time that was simulated before was only this, like it's just 1/10 of the simulation. So now we can see there's a wide range of transition between the two states. And now to look at, let's say, so now we can see there's much more transition in the distance. Yeah, okay, now, as I say, we also want to look at, one thing we want to look at is we want to look at the height of the added Gaussian. It should go to 0. And this is, in this case, for like 1 CV is the 4th column, is this one here. And then we would just plot it like, this is plot the 4th column. And you can see here that this, I think should zoom out. So now we can see that this height of the added Gaussians goes kind of slowly to 0. And you can see there is always some, let's say, the variation in height, but overall it kind of decays to 0. So in this case, this just shows us that the simulation should be reasonably converging in the sense that we have a lot of transitions and the hill height is going to 0. And now the first thing that we can do is that we can obtain the estimate of the phase from the added Gaussian. Basically, we sum up the bias potential. And this is done with this command here, the so-called SUMHILL command. So, why is it? So this basically, so now we just make a different folder for this file. And now we run this plumed SUMHILLs, and with this dash hills, which is just the hill file that we're using. And then we just define the output file that we want to write this out. So I'm using this run plumed command to kind of wrap it into, so we don't need to type the full command every time. And then we also, let's say, by default, the fares that we get from this SUMHILLs will not have the minimum at 0. And this is a bit, it's not so easy to compare two results if they don't have the same minimum. So, because just to keep in mind that the fringe surface is defined up to an arbitrary constant. So you can always add a constant to the fringe surface to make sure that its minimum of the fringe surface is at 0. So this is just what we do by adding this min 0 flag here. Okay, now we can see that, okay, we basically summed up this like 10,000 kernels, meaning the biasing kernels, and yeah, so this writes out the insert. And also we can see that, let's say, the sum hills has various other options that one can use in many cases. For example, if you want to have like different minima and maxima of the fringe surface, different number of bins of, let's say, how often the file is, let's say, how often you calculate the fringe surface on the grid and so on, and various other options. We'll see more about this later on. So now we have this fringe surface and we can plot it. So we can basically, let's say, plot the, we can just load the fringe surface with this numpy load text file here, and then we plot the fringe surface as like in this way here. We just plot the first column, which is the distance, versus the second column, which is the fringe itself. We can see just by here, if we do, let's say, I will just show you how the header of this file looks like. And you can see here that this, like, the first column is just the distance, then the frequency, and so on. And this is like, will show how many bins were used in the calculation. You can define this yourself if you want to have like a fringe surface on a binary grid. Okay, I forgot to. I forgot to do this calculation on this, run this cell here. What I was doing here was not strictly needed, because what I will do, I will just divide the fringe with kpt. So I show the kpt in units, show the fringe surface in units of kpt instead of kilojoule per mole. So this is the fringe surface that we get from a simulation. So we can see here we have the minimum for the associated state, then the dissociated state, and we can see that they, let's say, that the dissociated state is much broader. And here we can see that the fringe surface starts to go up, and this is due to the wall that we add to the simulation. So in reality, like the fringe surface should go a bit further here, but it doesn't really matter in this case because we're just using it for, let's say, educational purposes. But in this case, like, so we can see here the barrier, and if you would try to compare this value to this value, you maybe see that this is approximately the barriers are approximately 5 kpts. Okay. Yeah, around 5 kpts, because this frequency is in units of kpts. And as you can see here, as I say, we're plotting it as a, like, here we just don't do any shifting of the potential. But what we can also do, just to maybe easier to like estimate the barrier regions and so on, so that we can calculate these gas min to 0. And then we have minimized, so in this case, here we have put the minimum at 0. Just gonna add some limits so it's slightly easier to see what's going on. Let's say 10, maybe. So here you can see, okay, that the barrier is around 5 kpts, and in this case, let's say, yeah. So we can see that this is the fringe surface, so it's easier to But now what we did is that we only looked at the fringe surface at the end of the simulation after 10 nanoseconds. But we want to look at, if we want to look at how the fringe surface behaves during the simulation, basically see the time dependence of the fringe surface, of the estimated fringe surface. So we can do that by adding this flag stride 1000 to the SumHill tool. So what we do now is that we instruct the SumHill to every 1000 added Gaussian recalculate the fringe surface and write it out to a file. So in this way, we can easily compare the different fringe surfaces. So we just create a new folder for that, and then we run the simulation. And yeah, okay, it didn't give me output because I was not asking for it. Okay, so now we have generated these fringe surfaces, and now we can plot them together on the same plot and compare them. And this is what I'm doing in this, say, script here. So this is what we're seeing. So this, we have always aligned all of the surfaces to the same minima. And now you can see that after around 1000, 2000 picoseconds, all of the different surfaces kind of converge to the same, let's say, are in close agreement. So you can see there are some fluctuations here, but they are not so large. So this is something what you always should do, is to look at the fringe surface as a function of time. Not only look at the end of the simulation, but really as a function of time, like every 10, let's say, with some given stride, depending on how long your full simulation time. You should always look at the convergence in this way, because it can happen that your fringe surface at the end if it's fluctuating a lot, you could just be lucky that it's in agreement with something with what you're expecting to get. Okay. So another thing that we can do now is that to kind of gauge the convergence is to look at the fringe difference between the two states. And so what we need to do is that we need to integrate over the probability of the two states. And this is something that Michael mentioned in his lecture yesterday, is that we need to, let's say, integrate over the region of the two states. So we want to calculate, let's say, and we want to take the fringe difference, which is the log of the ratio of the probability of the two states. And so to do that, we need to define where we kind of separate the two states. And this way, the best way to do that is to look at the probability distribution. So in this case, the probability distribution according to the series is just like the negative, it's the exponential of minus beta times the fringe surface. So this is what I do here. And here I have this value to, let's say, for diagnostics, I use this value to separate the two states, like 0.36. And we can see that value separate the two states pretty well. So we can see here that here the probability is nearly 0. So this value should be good value to separate the two states. So if we say that this is the below a distance of 0.36 is the associated state, and above is the dissociated state. And then we just need to integrate over these two states. So this is what I do in this function here. It's a very simple function, and it just calculates the probability and then sums them up depending on the location. And it's a very simple tool. And what we do now is that we run, let's say we do another similar to the SumHills with a stride of 10 to get the fringe surface every 10 added Gaussians. And then we can do that. And now we can just loop over these different fast files and plot the results. So now we will see it basically the fringe difference as a function of time. So we can see here the result, meaning the converge, and we can see here how it the fringe difference is behaving as a function of time. It's not really perfect result, and I think that is because because here one of the issues might be that the sigma that we're using works well for the associated state, but it's a bit too small maybe for the dissociated state. So sometimes the meta-dynamics bias has a bit of difficulties to fill up appropriately in the dissociated state, which might explain this like fluctuations in the fringe surface. But still, like it's okay. It's a reasonable kind of convergence, and probably you would, in this case, one might want to use something like adaptive Gaussian meta-dynamics to be able to have, let's say, sigma value that fits with the two states better. But at least in this case, it is, let's say, it's not fluctuating greatly, and it's, let's say, so this is kind of a reasonable behavior. Okay. So this is, let's say, look at the fringe surface. So now let's look at the reweighting procedure. And that is the other way. Let's say here we calculated the fringe surface directly from the bias potential, but now we want to use reweighting to do this. So now we need to look at this, let's say, our bias that we calculated. So as I say, we can use this kind of reweighting procedure where we cannot do a reweighted histogram, where we add each point like we do, like we add points to the histogram, but we use the weight, also incorporate the weight when we add the points. So it's a weighted histogram. And for that, we need to use this R bias, because this is like this renormalized bias with this C of T factor. And to see the behavior of these different values, let's look at this plots here. So you can see here, the direct meta-dynamics bias is always growing, but it's really always growing like a modulo constant, because it's really growing. But if you would, let's say, take a constant out from it, like a time-dependent constant, this bias has really converged. It's just like, because you're always adding small Gaussians, so never is always like ever growing. So it like will always grow. But you can then calculate this R bias, and you can see that one seems to converge pretty well. So now within, let's say, 2000 picoseconds, like the different, let's say, this R bias has converged. And that's because the C of T, this factor here that you calculate, exactly kind of cancel out the growth of the meta-dynamics bias potential. So this, like, so for the reweighting, we need to use this R bias. Okay, so as we can see here in this initial phase of the simulation, the bias is fluctuating a lot. So you need to take care of that. So the way to do that is by, let's say, what we normally do is that we ignore some initial part of the simulation where the kind of the bias is changing much more rapidly, and we would, let's say, the weights might be unreliable. It's like there's kind of a equilibrium period that we need to obtain. Like we need to kind of equilibrate the system somehow. You can think of it like that way. So yeah. Okay, now what you can do is that you can use this weights and the samples to do a weighted histogram. You can do that in Plume directly by using this input as shown here. So this is something which we just do in post-processing. We don't need to use chromers for this. So we just read in the different color file, and we calculate this histogram here. So here we are using a discrete histogram with a bin with 100 bins, and here we use this weights that obtained for the meta-dynamics bias. And then there's just the commands for like calculating, converting to a FAS and writing that out. I should note that in Plume you can also use like a kernel density estimator with Gaussian kernels to smooth the result, but you have to be careful with that because you can over smooth the result. But in principle, you can do that also. But here we just use like discrete histogram. So what we do now is that we want to make sure that we are not, let's say, skewing the result somehow by including parts in the beginning that can influence the result. So what we do now is that we perform simulation where we ignore different parts of the simulation, initial part of the simulation, and calculate the fringe surface. And this is what I do here. I use this kind of trim color file Python script that will be based on like how much you want to reduce from the color file, and spit out a new color file where it has, let's say, been ignored. And then there's just different commands that do all this plotting and so on, and we'll get like the different results. Wow. Okay, I forgot to create a plumbed file, which is needed. Okay, I forgot to do this also. Now we just run this command. But we can actually see in this case, if we trim, let's say, 100 to 1000 picosecond, we get the same result. So in this case, it's probably fine to ignore, let's say, we don't need to ignore so much. We can also double check the result. We can go to 2000, maybe to 500, and see the result, how it behave like. And you can see if we ignore up to, let's say, 0 to 2000, it doesn't really change so much the result. But this is still a check which is always do, is that how much you should ignore of the initial part of the simulation when doing reweighting. Okay. So in this case, we just decide to use like 500, and now we can run this, let's say, simulation and run this like reweighting. So now what we can do is what we should do is that we should compare the bias obtained directly from the bias potential. Sorry, compare the fringe surface obtained directly from the bias potential and the one from reweight. And just to simplify this, I just define this function for plotting different phases. One can do it also directly. It's just I like to define these functions to like simplify the you can just call them. So now we just let's say we define this function. So we plot the fringe surface from the bias and from reweighting. And as you can see, the fringe surface are in reasonable agreement. They were in better agreement when I did run this before. I think it depends slightly on the random seed used for the simulation, but you can see that they are in reasonable agreement. Meaning they are not in perfect agreement, but they are in reasonable agreement. Most of the time when I've run this notebook actually has been in better agreement than this, so it's a bit interesting. But yeah, but at least this is, let's say, this is an okay agreement. Let me double check that I was not using a different sigma than was explained. Okay. But in this case, I think this looks fine. Maybe you want to do is that maybe you want to run the simulation a bit longer to converge the result better. But I think the main issue here is that this Gauss, like here, the surface is kind of smooth, but here you can see a bit of roughness in the surface because the Gaussian added are a bit, maybe a bit too small to get a smooth estimate of the dissociated state. Okay, so now we reweighted on the CV that we're biasing, but we can also do is that we can reweight on both the distance and solvation CV. And yeah. And this is something which, let's say, we can also reweight on CVs that are not biased during the simulation. So we can do it here. It's the same as before. We do a plumbed file where we read in the color file. And then we have, let's say, distance. And like now we have a histogram with two variables, the distance and coordination. We define the grids for the histogram. And now we also define bandwidth for like a kernel density estimator. And these are some values that were, let's say, obtained by trial and error in a previous tutorial. So we can just use them here. And then now we have basically used this to generate a two-dimensional surface. And now we can, let's say, use this the function here. It's slightly bit funky because this is just how one needs to do when converting the fast file from plumbed into something which you can plot with matplotlib. And this is, let's say, the fringe surface that you get from, in this case here. So in this case, you have the fringe surface as a function of this, let's say, the distance here on the x-axis, and the y-axis, the solvation of the sodium atom. Okay. Yeah. So now, basically, this is the analysis one can do when we're doing merodynamic simulation. So now what we want to do next in the next exercise is to do another merodynamic simulation where we bias both the distance and the solvation. In that case, we should get a better estimate of the full fringe surface than here. Okay, so now we just create a new folder, do all of the different actions to run it. Maybe let me see. Yeah. And now we just need to define, let's say, merodynamics action with. Now we define a merodynamics action with, let's say, two corrective variables, the distance and the coordination. So now we need to define also a sigma value for like the coordination. A good value will be 0.1. And we also need to define the grid for the coordination number, or the solvation CB, sorry. And then we run the simulation. This one should take about slightly less, 5 minutes, 6 minutes, hopefully. And yeah, and that should, then we should be able to kind of cover, go at least to the restarting. So maybe now, since we're waiting for the simulation to finish, then maybe you should, if someone has questions or something like that, we can maybe use that to answer any questions people might have. Let me see what is in. Okay. Okay, someone like the last question, when the energy barriers for a system is very high, like retinal photoinformation is like, yeah, extremely high. So in that case, for sure, a bias factor of 5 is not enough. Then you most likely will need to use larger bias factor. So there is, let's say, is there a highest bias factor that one could go for? Yes, meaning you can't just use normal merodynamics, and which correspond to a bias factor of infinite. But this then is like has some other convergence issues. So often people use easily bias factor of maybe 20, 40, 60, and that's fine, maybe 100. So in the case, if you have like extremely high barriers, then yes, you should use a higher bias factor. As I say, like there's a good question was answered already, a good answer already, like with the bias factor, it's a bit like a chicken and an egg problem, that like you don't always know exactly what is the estimated bias height before, but sometimes let's say you will try at different runs, and in principle, if you if you start two separate merodynamic simulations with maybe different bias factor, they should always converge to the same result. So one might take longer if a larger bias factor, but they should always converge to the same result. So you can always, let's say, try different bias factor and see what's going on. So it is always a bit trial and error with this bias factor, let's say, what value you should use. So it's not always so, yeah, I mean, you need to play a bit around. Then let's say, I would say when you're doing, like for most methods, when you're doing this type of enhanced sampling simulation, it's just, you're not just running one simulation, it's already a bit trial and error, finding the best parameter for convergence. So you might need to try a bit few different runs. It's never really like a black box that you can just submit one run and you get the result. Yeah. Fluctuation dominated. I'm not totally sure what you mean by fluctuation dominated in the last question. Meaning, let's say, with the bias factor, meaning, say, like was already answered, like 100 people have used bias factor 100 in published result, and is normally fine. Like, it take a bit longer to converge, but at least sometime it will yeah, like, how to say, like bias factor 100, if it's needed to enhance the fluctuation enough to overcome the barriers, you will need to use that. But the fluctuation dominant is the colors noise pushes the simulation. Okay. I think, meaning what you want, of course, I'm asking the question of Jason Wiley. I think you want to maybe you want to have diffusive behavior in CV space. So I think you can maybe over bias the system, but I'm not totally sure about this particular example to be to answer that in a good way.
No, I think it may have been too off topic. I'm sorry. I thought it would be a good question, but
no, it's like, you mean that basically the system is like going between all the different states, or?
yeah, so colored noise, we use it in coarse grain models, but it you use it to kind of in the bistable energy example that you used at the beginning in explaining this. The color noise pushes the simulation over the hump, so to speak. But if you use too high of a parameter, the simulation continues to just jump humps without ever stopping. So
this might be a little too distant from this particular method, because there you're using the momenta to change things, right?
Correct. Right. Yeah, it's
the potential. So
it's not very specific. It kind of blasts the entire system instead of looking at one individual.
And by colored specifically, you mean like low frequency?
You choose that. You choose.
Right. Yeah. So that might be a little beyond the context of the
I realized it after I asked. So my apologies.
There was someone who asked me directly, like, does the same meta-dynamics and reweighted result, if you get the same result for the directly from the bias and from the reweighted, is that sufficient to prove that the FES is correct? No, we cannot really say that. We need, like, these, like, it's very difficult to prove that the FES is correct. So what I think, my opinion, what you should always do is let's say, you should always run more than one simulation. Maybe you can run more than one simulation with the same setup, and if they converge to the same result, that is probably an indication that is like it is reasonably correct or reasonably accurate. But I think you should also try to vary the meta-dynamics parameters, because if you vary all the different meta-dynamics parameters within reasonable range, they should always give the same result. The result should not depend on the parameter. So I think it's very difficult to prove that your free surface is correct. Meaning you can maybe estimate some with some accuracy, and maybe I should mention, like, I didn't talk about this way, but there is a good tutorial in the Plumed masterclass about, let's say, how to get error bars on free surfaces, because I think this is a good way to think about it. Let's say here I was only showing basically the free surface, like free surfaces, but of course what you should try to do is you should try to get error bars on your free surfaces, and there's a way to do that through reweighting, which is discussed in one of the plumed master classes. But this is a bit beyond what can be discussed in this, like in tutorial, like here.
I think one thing about proving that a free energy surface is correct, for any enhanced sampling method, it's important to understand that you can never like prove that you've gotten all the slows of degrees of freedom, because it's basically, you can't see what you don't see.
Yeah.
Like you can never prove there isn't some other slow degree of freedom with every in this thing in the system completely rearranging with barriers that are 1,000 kBT out there.
Yeah.
So all you can do is demonstrate that everything is consistent with it being the right free energy surface.
Yeah, I think proving is maybe the wrong way to think about it. I think it's like you can use various ways to, let's just show the reasonable statistical accuracy that the results that you're getting kind of are accurate up to some degree.
Yeah.
But
is it self-consistent with everything you've done? That you can check.
Yes, and that is a good way. I think you should always run multiple simulations and always try to vary the parameter to make sure that there is no dependence on the parameter and so on, because there should not be dependence. But okay, so now
I just want to add that just because you have convergence also doesn't mean that you have the right answer, especially for some of the rugged energy landscapes. So you may be converging, but you may be missing certain transitions completely.
Yeah, definitely. I mean, I think, as I say, I mean, there could be missing degree of freedom, which is correspond to a huge barrier, which is you're completely missing. But you can, of course, there can also be various things. So it's like, I think it's difficult to be totally sure that you're getting the right answer. And I think okay, now we have the simulation run. So now we pass these two collective variables. So now we can look at the, let's say, what's going on? No, oh, stupid. Yeah. I did something stupid. I started the simulation again. Now I can solve that. Because what Plum does, if it starts the simulation again and there's always a Hills file and a Colver file there, it backs up them. So what I can do now is that I can make sure that I just rename the backup files. And now we should have the correct files, at least for the analysis. So now we can see that we have these files and we can plot them. So now we can see again, the distance is like started to be diffusive, and also the coordination started to also kind of revise the coordination that is also diffusive. And now we can see the height. Since we are running a shorter simulation, it takes a bit longer. And also since now we are filling a two-dimensional surface, there are more places in the surface where there's no where there has no bias been added before. So the height will naturally take a bit longer to go down, because in 2 dimension is more volume to fill with the Gaussians. Okay, so the thing is that if you just directly look at the 2-dimensional surface, it's difficult to gauge the convergence, because in my mind, I find it very difficult to look at 2-dimensional surface and understand what's going on. So I prefer, in this case, to gauge the convergence by looking at the 1D projections. So this you can do in some hills by using this flag here. where you kind of just calculate the projection on a given collective variable. And then you can, in this case, you also need to give the KPT. And this is what is just done here. And this is what I did in these two cases. So now we can look at the convergence of the phases in this case here. So in this case here, we can see like the one after 1,000 picosecond is let's say not a good agreement, but after a while, at least for the barrier, the different surfaces are, let's say, in good agreement with each other, a reasonable agreement. Let's say there are some fluctuations, and in this case, one will probably need to run the simulation a bit longer. But we can see at least there is, let's say, there is at least for the barrier, but this area is slightly needs a bit more sampling to converge. And we can look at the same at the projection at the, let's say, solvation CV. There are some fluctuation, but let's say after like around 3,000, 4,000 and 5,000 picosecond, they're in better agreement. But you still probably need to sample this system a bit better. Okay, so yeah. So as I say, it's very difficult to look at the results directly from the like the two-dimensional surface and understand the conversion of that. So it's better to look at these projections in this case. Okay, and now we just we calculate the projections, and we can also calculate the reweighted phase for the distance as before. You can do the same as before, and then we can look at let's say we can also look at how the R bias value look like, just to maybe understand how much we should trim from the beginning of the file. In this case, maybe we should trim, I don't know, 500 to 1,000 picoseconds. But yeah, but we can also here we could do the same trick as before to, let's say, trim different values and see how it behaves. But in this case, we can just ignore the first 500 picoseconds of the simulation. So we do the same reweighting the same as before. We just read in the define this Plum file, and we read in the driver, let's say with this Plum file, and then we use this driver and use this like no atoms option to do this reweighting. So this is just post-processing. But I would note that in principle, you can also use this weights in any NumPy function histogram that can do a weighted histogram. It's just I find it convenient to do it in Plum because this is how I have been doing it. Okay, so at the end, so now what we have obtained is that we obtained, let's say, the phase from the by biasing the distance directly from the bias potential, from the reweighting when biasing one CV, directly from the bias potential when biasing two CVs, and from reweighting when biasing two CVs. So now we have like three different estimates of the fringe surface as a function of the distance, and we can see these estimates here. So we can see there is still some, let's say, uncertainty in the let's say dissociative state. So probably we would need to run this longer to converge it better, and to, let's say, yeah, we generally probably need to run some of the simulation a bit longer. So yeah, so we probably will need to do that. So you can see there is some fluctuation. So like in this case, you can probably put some like in a very kind of ad hoc way, we could put some error bars on this, let's say, fringe surfaces here. But there are better ways of calculating an error bars that one can do. Okay, so then finally, we can calculate the two-dimensional phase obtained directly from the bias potential. And that is just obtained here. And this would be the two-dimensional phase that we obtain here. And this is, let's say, we'll just look at the color map, this is a reasonable agreement that what we obtained from the reweighting from the previous simulation. In this case, like this is just we just cut off the color bar at 10. This is why it's always white outside this region here. The region outside this is like correspond to regions in free energy that are higher than 10 kPTs. Okay, so finally, maybe we can do one thing, which is just to show you what you can do. Is like clearly in this case, we need to run the simulation longer. That the results that we get here, we probably need to run them a bit longer to get better estimates. So this is quite common, is that we often, let's say, we run initial simulation and then we see that, oh, we need to run it longer. Or another case is that often on, let's say, high performance clusters, you can only run like a simulation for like 1 day, 24 hours, 72 hours, so on. So you need to split your simulation in different parts. So most empty codes allow for some kind of restarting. And you can easily do this with Plume. So you just need to add like a restart to the plot to the top of the Plume input and restart the Morgan dynamic simulation in some way that is specific to the empty code. And now the Plume will just read in the previously added Gaussian and append to the Colvar file and the Hill file. For GROMACS, it's even easier. You don't need to do anything. You just need to restart the GROMACS in the way you restart GROMACS, and Plume will detect it's a restart and read in the Colvar file. So in the final minutes, I will just show you that here, this is just a way how you can extend a TPR file in GROMACS. Here we extended TPR file by, what was that, 5,000 picoseconds. And now we run the simulation. So this will take probably 6 minutes, so probably will not really maybe finish it this way. So in this case, what you can then do once this simulation is finished, and I will let it finish and will output the results, is that you can do the same analysis as before and obtain, let's say, let's say a better estimate of the free energy surface. So you can do this or the same analysis as before that we did here. Okay, so yeah, and this is, I forgot something. What did I forgot? Because I made this mess before of restarting the run. Okay, now it's running, but I don't know if we have time to look at the results because we already started to be out of time. But I will maybe want to show one thing is that in this case, when we are restarting, is that if we look at the to like grab, what was it, command? We look at the log file of GROMACS. If we can do like we can grab the log file of GROMACS and search for this keyword here. So now we can see in this second run that Plume started, like GROMACS started, we read in the 5,000 Gaussians. So one can see that the let's say the Gaussians have been read incorrectly. So in this case, one should, let's say, get the like the initial bias from the Plume will read in the Gaussians, so we'll reconstruct the bias from the previous simulation, and we'll restart adding the Gaussians. So you can split the simulation into different parts. You can restart the simulation and not lose the information by the the meta-dynamic simulation. Okay, so this was more or less what I wanted to talk about today, like how to bias. How you start with an unbiased simulation, then you bias one CV, analyze the result and do reweighting, how to bias two CVs, analyze the result, and then like how you can restart the simulation. So at the end, I just added this, let's say, optional parameter exercise, is that if you're interested, you can start to try to vary some of the meta-dynamics parameters, like the bias factor. You could lose, for example, you could use a value of 2 or 10 instead of 5, and see how this changes the result. And you can basically use all the analysis tools that we did before, but you will just need to fill in the copy from the different cells to do that. So let me just see how, if we have, yeah, probably will take more than until 5 o'clock. So maybe if someone has, let's say, some final questions. Okay. Okay. There was a question like, with your first meta-analysis simulation, you just biased against the distance and were able to get the fashion towards the solvation by reweighting. So what is the advantage of biasing both the distance and solvation if it takes longer to converge? I mean, it can be cases that, let's say, you might want to get better sampling and, let's say, extended sampling of this other collective variable. So, like, okay, in this case, the solvation is not really that, meaning the solvation is coupled to the distance, but the solvation is a fast degree of freedom. So in this case, you don't really need to bias it. But what you could gain by biasing it is that you might maybe see further areas of the free energy surface that you don't get when biasing only the distance. Because you might, as you bias the coordination number, you might start to bias, let's say, some areas that are, let's say, some areas correspond to the solvation that are kind of rarer, but like, so you might get a bit more sampling of the two-dimensional surface. So this might not be a good example of that, because sometimes you might reweight on a CV that is like maybe somewhere in between being like a really slow CV and a fast CV, and you want to get like a better description of that, like the free energy surface corresponding to that CV. And yeah, okay. What is the difference between bias and R-bias again? Okay, the difference is that the bias in meta-dynamics is always, let's say, where is it? The bias in meta-dynamics, this is the bias directly. This is always growing. So the issue is that you cannot use this directly in reweighting, because what will happen there is that because the weights in reweighting depend on the exponential of the beta times the bias. So if you would use this directly for reweighting, you would basically only get contributions for the sample with this weight here. Like the sample here will just have 0 weight. And this will anyway give the wrong result, because you're not taking the time dependent of the bias potential into account. So what you do is this, like this RCOT, this is called COT factor. And this is like a time dependent constant that like normalizes the bias potentials. So in this case here, when you calculate it, so this R bias is basically the bias minus this value here. So you can see that this constant is growing the same way as the meta-analysis bias potential, and then you obtain like the R bias here. So when you're reweighting meta-analysis simulation, you should always use the R bias, and this is also calculated on the fly during the simulation. There is another bias, like the reweighting factor in meta-analysis called a procedure called the last bias reweighting. And this is discussed in some other tutorials. So there are other methods to do the reweighting where you don't need to calculate the COT. And okay, then there's another question. When should you use well-tempered meta-dynamics opposed to umbrella sampling? That's a bit, I think that's a bit, but I don't know what's a good answer to that. That depends a bit on, some people prefer different methods. That's maybe a good way of saying it. one issue is that, okay, I mean, I haven't really used umbrella sampling myself that much, but meaning my feeling is that if you have like more like 2 CVs, it might take a bit, you might need a lot of windows to cover the like the fringe surface sufficiently. But so meaning I have a preference for meta-dynamics, but other people have a preference for umbrella sampling.
So one thing about umbrella sampling, the traditional way it's defined is basically you pin your simulation to various points, various values of the collective variable. And so that guarantees you'll visit those values of the collective variable. But one problem is when you pin something to a collective variable, you can create barriers that inhibit the sampling. So with any method that essentially varies what the value of the collective variable is, you get a chance to avoid a lot of those barriers, if that makes sense. But you generally want it to be visiting each simulation to be visiting different values of the collective variable, as opposed to each one pinned down. Umbrella sampling has fewer things. Umbrella sampling is simpler though, and sometimes complexity has lack of complexity has advantages.
Yeah, I mean umbrella sampling also has like the issue of the collective variable. Meaning there are ways to diagnose umbrella sampling if it's missing collective variable, like, but this is also like they're like ultimately they both depend on having good collective variables. And meaning, yeah. Okay, so finally, since the simulation run, so the distance we can see now just after like we continue the simulation, and we can see that the height went down to kind of somewhat 0, but it went down a bit further. And now if we compare the, let's say, the sampling, it's converging somewhat, but still, if you compare like the different surfaces, they're they're not in full agreement. Which is interesting because every time I run this before, the result looked better than this, I have to admit. So there's a bit, the results are a bit, they're not always the same because there's a different random seeds, but yeah. So when I did it like in front of people, it like, it's not as good as before, which is funny. Okay, so what am I doing? And then also, yeah, okay, this is just the final thing. It's just to calculate the phase as the 10 nanoseconds. Okay, so I think we're out of time, and yeah. So, like, if you want to learn more about doing meta-dynamic simulations, I mean, I would recommend look at the various tutorials that are online, and which you can look at, and with different systems. There's a lot of tutorials, let's say, like now I didn't really go to all of the details, like say how to select the atoms, and like there's various ways of doing that in let's say, for example, if you want to select all the C alphas in your system, like you can simplify the selection in some ways doing that. So like there's a lot of selection syntax for atoms that is good to know. So this really only touches upon really very shallow on what you can do with the prompt and what collective variables are available. Yeah. But so I think this like concludes what I want to discuss. Like if someone is interested, people can look at other more like other systems, and yeah. So then look at, let's say, this exercise 4. What I will do, what I will do now is that once this has finished now, I will save the notebook and add a notebook with a solution to the GitHub. And I will also add the solution, let's say all the exercises that we did. So the files are already also there. So okay, yeah. So I would just like to thank you for today, and hopefully hopefully you learned a bit about how to use hemodynamics. But I would emphasize let's say, that how we did it today was not really how you would interact with a normal simulation. This is more like for educational purposes, but the main difference is that you would submit this simulation to a queue, and then you would, let's say, do but the analysis is very similar. Like you can do all this analysis step what I did, and I can show that. So so you can use some of the functions and stuff that is defined in this tutorial to do an analysis of meta-dynamics. And tomorrow there should be a tutorial how to do meta-dynamics using multiple walkers, and that is something which can help to improve the convergence, because you have multiple walkers sharing the bias potential and Gaussians and so forth. Yeah, as I say, meaning there was someone asked me about the other tutorials. There are basically also in the slides and also in the GitHub README file, there should be some links to tutorials, but I can add, let's say, links to tutorial which are the best to start on if you want to learn more about Bloom. Okay, so thank you for today.
Thanks, Omar, and thanks everybody. We will pick up again tomorrow at the same time we started today, and we'll be discussing more about sort of replica exchange families of enhanced sampling, which captures a lot of the same ideas, but meta-dynamics, but with different approaches. So thanks, everyone. We'll see you tomorrow. Have a great late afternoon and evening.
Thank you.
Any other logistics people? Well, we've lost already 2/3 of the people, so we'll cover logistics tomorrow. Bye.
Michael, I think you should just blanket email one more time. I think it looks like we only got 2 more people to do it, the evaluation piece.
But we should
Just
blanket.
email everyone and say if you haven't done it.
Yes, okay. Sounds good. I will do that. All right, I'm gonna end the call now.
Okay, thank you.
Bye.